1 minute. First, Jay sir will introduce you and he will request you.
Okay.
Yes, Jay, you can start.
Okay. Good morning, everybody. Today, on a very auspicious day of Christmas. So, first of all, I would like to wish everybody Merry Christmas, Happy Sunday. And I'm very happy today that in our PhD webinar series, we are having our 20th speaker today. And in this PhD webinar series, we, Microbiology Society of India, are giving memento and certificate to every speaker. And we are doing this series to for the upliftment of the subject. First of all, I would like to express my sincere thanks and gratitude to All India President Dr. Arvind Deshmukh sir for providing us this valuable platform. I request Deshmukh sir to speak few words.
Okay, thank you. So, I'm very happy to speak today. The reason is that our lecture series is continuously going on. And we have now many lectures stored on our YouTube channel. And like Jasprit, there are many young people in India doing hard work, doing research, and moreover, they are eager to present their work to inspire others. It's the happiest moment for Microbiology Society to give them opportunity on our platform. And I really appreciate Aishwarya Badguzar, please close your mic. Please. Mic, please. I request others to please mute your mic. So I appreciate Jasprit for presenting today the research work. And I appreciate the efforts by Jay sir every Sunday regularly. And today, again, you see 31 participants have joined. And some senior teachers like Dr. Kalindi Shinde, Dr. Santosh Jha, then Dr. Shahnawaz, Dr. Prakash Halami, and Swarnajit Singh. Like that, senior peoples are always there to appreciate these young generation. Thank you, everyone. Now over to Jay sir.
Thank you, Deshmukh sir. Thank you for your valuable words. Now I would like to introduce and welcome our today's speaker, Jasprit Kaur ma'am. Dr. Jasprit Kaur ma'am has done her integrated master's program from Punjab University, Ludhiana. Ma'am is currently working as project associate at Punjab Agricultural University, Ludhiana. I welcome Jasprit Kaur ma'am to start her valuable lecture.
Okay, thank you, sir.
And excuse me, I request everybody who are not speaking, please mute yourself.
Yes, sir.
Good morning to all. I am Jasprit Kaur. So I've completed my PhD in biochemistry at from Punjab Agricultural University, Ludhiana, and now working as a project associate at School of Agriculture Biotechnology, PAU Ludhiana. So during my PhD, I have worked on the biofuels from production of biofuels from lignocellulosic waste. So during PhD, my project title is Utilization of Sugarcane Juice and Bagasse for Bioethanol Production. So today I'm here to present PhD webinar on utilization of sugarcane juice and bagasse for bioethanol production. So sorry, sir, this.
No worries, ma'am. Please take your time.
So let's start with some introduction. As we know, India is heavily dependent on the import of crude
Jasprit,
oil.
I
Yes,
request
sir.
you,
Yes, sir.
you can start your video also,
Okay.
if possible, if possible.
Okay.
Yes, very good, very nice. Yes,
Heavily
proceed.
dependent on the import of crude oil. So as we know, India is heavily dependent on the import of crude oil to meet domestic energy requirements of petroleum products. The consumption of the petroleum products in India is increased with a growth of 0.4% during 1920 as compared to 1819. So ever growing dependence on petroleum for transport sector will be the key reason for India to look for an alternative energy sources. So in this renewable energy can therefore play a vital role in meeting energy requirements in a sustainable manner. So cellulosic ethanol is a potential option for meeting biofuel requirements due to large biomass availability in the country. So as we know, lignocellulosic waste is there the massively produced every year through forestry or agro-based industries. And the disposal of these wastes is a main challenge. So because much of these plant-based material, they are often likely to be disposed by burning, which leads to the production of the greenhouse gases emission that causes some serious environmental pollution issues. So currently, lignocellulosic biomasses have acquired special research importance owing to their wider availability and biorenewable nature. So these lignocellulosic wastes that include the rice wastage, sugarcane bagasse, corn wastage. So they can be converted into, they can be used for the production of various biofuels, biomaterials, and some value-added chemicals. So as the diversity of the biofuels depending on the source of feedstock that is used for biofuel production. For example, if we use some edible biomass like sugarcane juice, it comes under the category of first generation biofuel. And if we use some non-edible biomass, the lignocellulosic bases, they come under the second generation biofuels. So as a sugarcane is a photosynthetically one of the most efficient plant with a high net energy ratio, and the biomass produced by this biomass is double than any other crop that provide the lignocellulosic feedstock for second generation ethanol production. Globally, India is the second largest producer of sugarcane after Brazil, and it produces the bioethanol from sugarcane molasses, a byproduct of sugar. And the annual supply of molasses is sufficient only for producing approximately 2.7 billion liters of ethanol, but only a minor share of this is available for fuel use, which necessitates to look for alternative options for bioethanol production from sugarcane. So, sugarcane bagasse, it is an abundantly major bioproduct of the sugarcane that can be utilized for the production of bioethanol as it has high cellulose and hemicellulose content. So, from 1 ton of processed sugarcane, an estimated production of 2 kg sugarcane bagasse is generated. And this fibrous largely consists of a major constituent that is cellulose, hemicellulose, and lignin. So bioconversion of this biomass involves the three important steps, that is pre-treatment, enzymatic hydrolysis, and the fermentation of sugars. The pre-treatment is used to break down the structure of lignocellulosic biomass, that is cellulose, hemicellulose, and lignin. Then in the enzymatic scarification, these component that is cellulose, that it is degraded into monosaccharide sugars by using the enzymes. So then in the third step, fermentation, these sugars that is generated from the enzymatic hydrolysis of the biomass, they converted into the bioethanol. So this is the outline of my work that I have been carried out. Thus, this study mainly focused on the selection of the sugarcane variety of leaf clones with a high cellulose content, and then the optimization of the ethanol production process involving pre-treatment, enzymatic hydrolysis, and the fermentation of the gas hydrolysate and juice for bioethanol production. So, as we know, if there is variation in the feedstock, it leads to the different ethanol production process requirements, even if it is for similar biomass or the varieties of the same species. And with this, we have planned our first objective. We have screened the different sugarcane varieties and clones for desirable traits required for bioethanol production. And in the second step, that is the pre-treatment, it is an energy intensive process that accounts for the total 20% of the total ethanol production cost. So for this, we have planned our second objective, that is to develop the most efficient process for pre-treatment of sugarcane bagasse. And as we know, for the enzymatic hydrolysis, enzyme is required for the hydrolysis of the biomass. So for the hydrolysis of the cellulase enzyme is required, and the cost of this cellulase enzyme is for scarification is the pre-treated bagasse is also very high and needs to substantially brought down for making the ethanol production process an economical viable option. So there is a need to identify a potent fungal strain that possessing the high enzyme title for efficient scarification of bagasse. So with this, we planned our third objective, that is to identify the efficient cellulase producing fungus for increased scarification of bagasse. And fourth objective is to work out the fermentation efficiency of the yeast for bioethanol production. With this, there's a development of we have worked on the development of an ideal process, biochemical conversion process that involves a pre-treatment, enzymatic hydrolysis, and fermentation of the sugarcane bagasse that can help to improve the overall economics of the process. So this is my first objective is to screen the different sugarcane varieties of leaf clones for energy traits that is associated with bioethanol production. For this, we have 29 different sugarcane varieties. They were procured from the regional research station Kapurthala, and the juice was extracted from these mature canes, and the percent juice extraction was calculated. So the sugarcane juice was clarified and analyzed for different biochemical parameters, and the bagasse of these varieties washed thoroughly and dried in hot air oven and sieved for the analysis of different parameters that are associated with the ethanol production. So this is the list of the varieties that are used for my research work. This first table shows the percent juice extraction and weight of the residual bagasse of different sugarcane varieties of fruit clones. So among different varieties, the percent juice extraction was ranged from 41.47 to 68.62%, with a significantly high juice extraction was recorded in the sugarcane clone, that is COPV 14185. So similarly, the weight was ranged
Hey,
from...
are you there? A lot of background noise is there actually. Yeah, you can continue the presentation.
So the weight of the residual bagasse among different varieties, it is ranged from 338.59 to 579.40 gram per kg cane stalks, with the maximum weight recorded for the clone CO 14222. So this graph shows the biochemical parameters of the juice among different sugarcane varieties of leaf clones. Among different varieties of leaf clones, the total sugar ranged from 13.62 to 19.09%, with the maximum total sugar was recorded in the variety COPV 92, and the sucrose content ranged from 13 to 18.55%, with the maximum sucrose content was recorded in the sugarcane variety COPV 92. The reducing sugar content ranged from 0.15 to 1.65%, and the titratable acidity ranged from 0.068 to 0.397%. The pH of the juice among different varieties of leaf clones, it is ranged from 5.15 to 5.99. So the maximum sugars were recorded in the COPV 92 variety were observed to be have maximum total sugars and the sucrose content along with the reducing sugar content of 0.54%. Titratable acidity is 0.07% and with the pH of the juice is 5.85. So this table shows the total solids, moisture content, and ethanol extractives of the gas of the different sugarcane varieties of leaf clones. Among different varieties, the total solid content ranges from 90.33 to 94.07%. The significantly high total solid content was reported in the sugarcane clone, in the bagasse of sugarcane clone, that is COPV 14181. The moisture content range from 5.93 to 9.67%, with a significantly low moisture content was obtained in the sugarcane, in the bagasse of the sugarcane clone, that is COPV 14181. The ethanol extractive content, it's a range from 7.23 to 24.97%. The significantly low ethanol extractives were recorded in the bagasse of sugarcane variety CO 14034. Some network problem. Okay, so this table shows the polysaccharide composition of the bagasse of the different sugarcane varieties. Among different varieties, the holocellulose content ranged from 62.85 to 70.70%, with the significantly high holocellulose content recorded in the bagasse of sugarcane clone COPV 14181. Similarly, the cellulose content was ranged from 33.80 to 39.55%, with the maximum cellulose content was reported in the sugarcane variety COPV 92. Similarly, the hemicellulose content ranged from 26.50 to 32.25%. And this table shows the total lignin content and the ash content of the bagasse of the different sugarcane varieties, leaf clones. The total lignin content ranged from 18.70 to 24.41%. So minimum lignin content was recorded in the bagasse of the sugarcane variety, that is CO0118, and the ash content was recorded in the variety of minimum ash content was recorded in the variety of in the bagasse of sugarcane variety, that is COPV 92. So we have then categorized the sugarcane varieties of leaf clones, identified on the basis of the different biochemical traits of the bagasse that is desirable for the bioethanol production. So among different varieties of leaf clones, the COPV 92 variety, it comes under all the category that is in the high holocellulose content, high cellulose content, low lignin content, and low ash content. So among different varieties of leaf clones, they screened the COPV 92 variety was observed to be the best sugarcane variety in terms of significantly high holocellulose and cellulose content of 69.75 to 39.55%, besides having lowest lignin content of 20.05%. So the juice of this sugarcane variety also contains the highest total sugar and sucrose content. So the bagasse of this variety was selected for the further experiments. So on the basis of the first objective, I made the one publication that is published in the International Sugar Journal, that is cellulosic ethanol production potential from bagasse of lead sugarcane varieties of leaf clones. So my second objective is to study the efficacy of different pre-treatment methods for delignification of the sugarcane bagasse. For this, the bagasse of the selected variety was subjected to the different chemical pre-treatment methods, that is acid alkali pre-treatment, sequential pre-treatment, that is acid followed by alkali, and the natural deputactic solvent pre-treatment. And this place shows the bagasse after different chemical pre-treatment methods. So we have recorded the different parameters after these different pre-treatment, that is polycellulose, cellulose, hemicellulose, lignin, and the ash content, and solid recovery of the biomass. So among different pre-treatments, the holocellulose content ranged from 62.70 to 87.05%. and the cellulose content range from 41.34 to 73.88%. Similarly, the hemicellulose content ranged from 12.39 to 21.36%. Among different pre-treatment methods, the significantly high hollow cellulose and cellulose content of 87.305 and 73.885% was recorded when the bagasse were treated with the 4% alkali for 60 minutes. Similarly, this table shows the total lignin content and the solid recovery of the biomass after different treatments. So among different treatments, the lignin content was recorded to be was ranged to be 9.09 to 25.69%. The lowest lignin content was recorded in the bagasse when it was treated with the 4% alkali for 60 minutes. And similarly, solid recovery was ranged from 29.1 to 61.26%. So then we select the optimum pre-treatment. So among all the treatments, significantly low lignin content along with high hollow cellulose and cellulose content was reported when the bagasse were treated with 4% alkali for 60 minutes. So this treatment was then selected for the further experiments. So as we know, by conversion of the cellulose in the pre-treated bagasse, it requires an enzymatic treatment where the cellulase hydrolyzes the glycosidic bond of the polysaccharide cellulose to yield fermentable monosaccharide glucose. So this process is commonly referred as scarification. So for the scarification, the cellulose enzyme is required, and the cost of this enzyme is very high, so needs to be substantially browned down for making this process an economically viable option. So there is need to for the production of cellulose, so there is need to identify potent fungal strain that possesses the high enzyme titer for efficient scarification of bagasse. So with this, we planned our third objective, that is isolation and screening of the cellulase producing fungi. So for this, we have isolated different fungal strains from different natural sources, that is soil, biogas slurry, compost, and decaying sugarcane bagasse. So then morphological and cultural characterization of these fungal isolates was carried out, and the qualitative screening of fungal isolate by using gram iodine dye, and the cellulotic index of the fungal isolates was measured. So this table shows the morphological characterization and the cellulotic index of different fungal isolates. A total of the 17 fungi was isolated from different natural sources. So among different fungal isolates, the fungal isolates that show the cellulotic index above 0.5, they were selected for the enzyme production, that is JS4, JS5, JS6, JS8, and JS17. So these five fungal isolates, they were used for the production of cellulase enzyme production under under liquid shake flask fermentation conditions. So this plate shows the qualitative plate screening of different fungal isolates by using the gram iodine dye. So the five fungal isolates that have the high cellulotic index, the optical microscopy of these five fungal isolates was carried out. And on the basis of the optical microscopy, the three fungal isolates, that is GS4, 6, and 8, they were tentatively identified as belonging to Aspergillus species. And the 5 and 17, they were tentatively identified as they are belonging to the Penicillium species. So the fourth objective of my study is to study the cellulase production by fungal isolates under liquid shake flask and solid state fermentation conditions. So for liquid shake flask fermentation conditions, the fungal isolates, which shows the high cellulotic index, that is 4, 5, 6, 8, and 17, they were used for the enzyme production under liquid shake flask fermentation conditions. So in the liquid flask fermentation conditions, we have firstly we have prepared the pre-culture suspension, and then we carried out the liquid shake flask fermentation for enzyme production. The enzyme was extracted for a period of 9 days at an interval of 24 hours, and the supernatant was assayed for different enzymatic activities and extracellular protein content. The enzyme activities that were recorded is the filter paper activity, CMC activity, salivase activity. So this table shows this graph shows the cellulitic activities and the extracellular protein content of the different of the 5 fungal isolates at different times of incubation. So in all the filter paper activities and the extracellular protein content, among these 5 fungal isolates, the fungal isolate that is JS17, it shows the significantly high filter paper activity, high CMCase activity, high cellulose activity, and the extracellular protein content. This table compares similarly in this table we show the comparison of different cellulose activities and extracellular protein content. So among these 5 fungal isolates, the GS17 fungal isolate shows the maximum filter paper activity, maximum CMCase activity, maximum cellulose activity, and extracellular protein content. So this isolate was identified to be the most promising isolates for the production of cellulase enzyme. Then then the solid state fermentation was carried out for a cellulase enzyme production from this fungal isolate that is JS17. So for this pre-inoculum preparation was carried out, and then solid state fermentation was carried out. The enzyme was extracted for a period of 6 days at an interval of 24 hours, and the supernatant was assayed for the enzymatic activities and the extracellular protein content. So this table shows similarly this table shows the cellulase lytic activities and the extracellular protein content under solid state fermentation conditions. So maximum filter paper and CMCase activity was recorded at 96 hours of incubation, and the cellulose activity was recorded at 72 hours of incubation. And the extracellular protein content was recorded maximum at 96 hours after incubation. So then we compare the cellulitic activities and the extracellular protein content from the fungal isolate GS17 at under liquid shake flask fermentation and solid state fermentation conditions. So we have found that the cellulitic enzymatic activities and extracellular protein content from the fungal isolate is significantly significantly high under liquid shake flask fermentation condition as compared to the solid state fermentation conditions. So we use the liquid shake flask fermentation condition for the enzyme production. So then we carried out the molecular identification of the fungal isolate GS17 that possessed the maximum cellulitic activities, and it was found that it showed the greater similarity with the Penicillium milloci based on the nucleotide homology and the phylogenetic analysis. So then the bulk enzyme production was carried out by using the fungal strain Penicillium milloci, and the enzyme was then the enzyme was concentrated by using the ultrafiltration. So then we check. This table shows the filter paper activity and the specific activity of the enzyme extract obtained after ultrafiltration. So we have found that the filter paper activity was purified by the 1.75 fold, and the percent recovery was recorded to be 67.39% when the enzyme was concentrated by using the ultrafiltration. So the fifth objective is the scarification and the fermentation of the bagasse bagasse hydrolysis for bioethanol production. And for the enzymatic scarification, we use the alkaline treated bagasse was scarified with concentrated fungal enzyme. So the different enzyme loadings, that is 5, 10, and 15 filter paper units per gram of the bagasse were tested, and the reducing sugar content and the scarification efficiency of the enzyme was worked out. So this table shows the scarification of the alkyl-treated sugarcane bagasse at different enzyme doses. Among different enzyme doses and the hydrolysis time, the maximum significantly high reducing sugars was recorded at 12 hours after incubation when the enzyme was treated, when the bagasse was hydrolysis with the enzyme units of 15 filter paper units per gram of the biomass, and the maximum scarification efficiency of 78.29% was recorded. So from the second and the third objective, we have made a one publication, that is valorization of sugarcane bagasse into fermentable sugars by efficient fungal cellulosic enzyme complex in the journal waste and biomass valorization. So then the fermentation of the sugarcane juice was carried out by using the yeast strain, that is Saccharomyces cerevisiae, that is NCM 3078, and the fermentation broth was then analyzed for ethanol concentration, total sugars, reducing sugars, sucrose, and the pH. So at different hours of the incubation, the ethanol content was increased from 0 to 96 hours of the incubation, and the decrease in the total sugar and the sucrose content was recorded from at different times of the interval. So the maximum ethanol concentration of 6.04% was recorded at 96 hours of incubation, with the sugar utilization efficiency of 67.32% and the fermentation efficiency of 90.96%. Then the fermentation of the scarified sugarcane bagasse hydrolysate was carried out by using the same yeast strain, that is Saccharomyces cerevisiae NCM 3078, and the fermentation broth was analyzed for reducing sugar content and ethanol content. So similarly, at different time intervals, the ethanol content was increased from 0 to 72 hours of incubation, and there is a decrease in, along with the decrease in reducing sugar content. So maximum ethanol concentration of 11.50 milligram per ml was recorded at 72 hours of incubation, with the sugar utilization efficiency of 66.47% and the fermentation efficiency of 55.93%. So then we scaled up the bioethanol production from sugarcane juice and bagasse hydrolysate at 1 liter scale. So in case of the sugarcane juice, the maximum ethanol concentration of 67.90 gram per liter was recorded at 96 hours of incubation, with the sugar utilization efficiency of 68.82% and the fermentation efficiency was 92.5%. So in case of bagasse hydrolysate, the maximum ethanol concentration was recorded 9.55 gram per liter, with the sugar utilization efficiency of 67.32% and the fermentation efficiency was recorded to be 53.81%. So then the potential of the ethanol production potential from 1 kg sugarcane stalks was calculated. So it was found that from 1 kg sugarcane stalks, the total of the 50.92 gram ethanol can be produced. So from this, I have submitted a one publication, that is fuel ethanol production from sugarcane, conventional versus advanced biofuels in the bioresource technology. So these are overall conclusions of my study, that is among all the early and mid-late maturing varieties, oblique clones. The COPV 92 variety was selected best variety in terms of significantly high hollow cellulose and cellulose content, low lignin content, and the maximum total sugars and the sucrose content in the juice. So in the second experiment, among all the pre-treatment, significantly low lignin content, that is 9.09%, along with high hollow cellulose and cellulose content was reported when the bagasse were treated with 4% alkali for 60 minutes. So among 17 fungal isolates, 5 fungal isolates, that is 17, 4, 6, 5, and 8, they were exhibited high cellulosic index, and the significantly high carboxymethyl cellulase, cellulose, and filter paper activities and extracellular protein content was reported in the fungal isolate GS17 under liquid shake flask fermentation conditions. So, and the molecular identification of this isolate GS17, it reveals that it has the greatest similarity with Penicillium millucci based on the nucleotide homology and phylogenetic analysis. So the cellulase produced from indigenous fungal strain resulted in the maximum reducing sugar content of 651.60 milligram per gram with the hydrolytic efficiency of 78.29%. The maximum ethanol concentration of 67.90 gram per liter was obtained from the sugarcane juice fermented by the yeast Saccharomyces cerevisiae at 96 hours of incubation. The significantly high ethanol concentration of 9.55 gram per liter was recorded from the sugarcane bagasse scarified with the in-house cellulase produced from Penicillium illogi. So the present study thus revealed the sugarcane in terms of juice and bagasse could be ideal used for substrate for bioethanol production using the optimized pre-treatment hydrolysis and the fermentation parameters. So these are the list of some publications and the conferences attended by me. Thank you.
Thank you very much, ma'am. Thank you. Now we are open for question and answer session. So anybody in the audience who has questions, please unmute yourself and you may ask the questions.
Joy, there are few questions in the chat box. First, you ask that questions.
Yes.
There are few questions in the chat box.
Okay.
So Prakash Salami sir is asking why low lignin and low ash varieties were preferred.
Sir, lignin is a basic barrier for the, as we know the structure of the lignocellulosic biomass, lignin is the main barrier for the bioethanol production. So we have to remove this lignin. So low lignin varieties should be therefore preferred for bioethanol production.
What about the ash?
Similarly, sir,
Low
the ash.
lignin, low ash. Yes.
The ash means there are some low ash varieties should be preferred for bioethanol production, as ash content was also is a main barrier for bioethanol production.
So this is how actually you look for a high cellulase and hollow cellulase and
Yes,
low
sir.
lignin and low ash content.
Yes, with the low lignin content. So because cellulose can be converted into fermentable sugars, so that we can produce bioethanol.
Yeah, the other question was actually what are the limiting factors? Why we are unable to use bioethanol very effectively in a commercial scale? You mean the conversion or the efficient fermentation technology or recovery?
The main limiting factor for bioethanol is the enzyme production. There is a law, the cost of the enzyme production is very high. As so we have.
Okay.
So this is there are the many factors that limit the bioethanol biofuel production, like pre-treatment cost is and the enzyme production cost is very high. So we have to identify some strains that produce fungal strains that can produce the cellulase enzyme production.
This said penicillium, which you are told is a novel with reference to the cellulose production. Is it very efficient? How do you rate it reference to the literature available one?
So penicillium, the fungal isolate that I have isolated, that it is much efficient than other isolates, Penicillium illogi, because it produces the high beta glucosidase activity as compared to the other like aspergillus and some other fungal isolates. So this is much effective.
So you want to tell a lot of enzyme work or the microbiology is required?
Yes,
So
the cost for enzyme production is very high.
Exactly. But this should actually grow in several agriculture and waste, no? To enzyme production should not be the bigger problem. With reference to the using the carbon source of the agriculture residues as a carbon source and looking for a better enzyme production. So a lot of work is needed from the microbiology as well as the fermentation angle for bioethanol, for efficient bioethanol production. What is your take-home message from this work, which is a very commercially important work?
So my important message is that we have to identify some strain, fungal strain. We can also work on some bacterial strains so that that will provide the enzyme, so that we can bring down the cost of the enzyme production process, and so that we can make this process economically viable for.
Wonderful, very good work.
Dr. Raja Gopalan is asking, why did you rush to scale up? Fermentation efficiency is around 56%.
Sir, actually, fermentation efficiency is 56% in case of bagasse. As we know, there is a enzyme this enzyme means the fermentation efficiency is low because of there is a there's a less sugars production during the enzymatic hydrolysis. So I have just scale of it at the 1 liter scale so that we can check how much ethanol production we can produce from, if we want to check out the economic.
ये पानी boiled है ना, ये पीने के लिए.
And also, sir, what would be the current production cost?
इतना ज़्यादा चाहिए होगा पानी? थोड़ा मुंह में डाल दो, मुंह में हाँ.
So, sir, we use the sugarcane for. I have used the sugarcane because it has the high cellulose and hemicellulose content. So, and I have worked on both the first generation and second generation bioethanol production from the sugarcane juice and bagasse. So, with that, can overall check the potential of this sugarcane biomass. So.
Okay, ma'am.
I want to ask one question.
Please, sir, please.
What are the benefits of using sugarcane, Jasprit?
Sir, the benefit of using the sugarcane is that in case of we can produce the both first generation and the second generation bioethanol from sugarcane. As in case of juice, we can produce first generation bioethanol, and from bagasse we can produce the second generation bioethanol production. So in the sugarcane bagasse, there's a high cellulose and hemicellulose content and low silica content. As in rice straw, if we can use rice straw, there is a high silica problem also with lignin. So in sugarcane bagasse, there is a very less silica content. So we can use this for bioethanol production. So as with the from juice, we can also produce the bioethanol.
Yes, this is very good work you have done. And are you working in Ludhiana or in Chandigarh now?
No, sir, I'm working at PAU Ludhiana at the School of Agriculture Biotechnology. But I have completed my PhD in biochemistry.
I see. So you're working in Ludhiana, not in Chandigarh?
No, sir, Ludhiana.
Very good, very good. Okay.
Thank you, sir. Jasprit ma'am, I request you to please type your email ID in the chat box.
Okay, sir.
Do we have any more questions in the audience?
Sir, good morning.
Good morning.
I have one question. I am Dr. Bharati, working as a professor in the Department of Biotechnology, Basveshwara Engineering College, Bagalkote. It's in Karnataka. We are also working on biofuels. Today, whatever the madam has given a good research information. Nice presentation, madam. I have one question. How it is different from DBT ICT technology, the 2G technology which government has developed it? I hope you know about the 2G technology developed by ICT.
Yes, ma'am. Ma'am, what is question?
That 2G technology, what we call cellulosic conversion, developed by ICT, Indian Chemical Technology. We call you have awareness about that? The cellulosic conversion to ethanol.
Yes, ma'am. Yes, ma'am.
Is developed by ICT also. The technology or the process is developed by ICT. ICT Mumbai.
Okay.
You tell the full form of ICP.
In Indian Chemical Technology, sir.
Right.
That is Indian Chemical Technology Institute. It is an institute. We call that technology as a DBT ICT technology only. The DBT
Yeah.
has funded and ICT has done a work.
ICT was known as a UDCT before few years.
Yes.
Sir.
Yes.
Yes, sir. The same institute. Yes.
Now
Yeah.
UDCT is now ICT Institute of Chemical Technology.
Correct.
I think
Right.
So how?
Dr. Kaur is not aware about that perhaps.
Yes.
Yes.
It's not in my mind, sir, actually.
Yeah, biochemical engineering goes, Dr. Lele is
So,
also with that.
Jaspreet,
Yeah,
Jaspreet, you can see online.
exactly.
Online, you can see and you can read about that.
Yeah, this is actually required for every researcher to update the literature available, and since this work has a commercial importance, what are the
Yes.
technologies developed?
Yes.
It is needed for us to update everything. And this is MBSI is acting as a very good platform to create this awareness and bring the common things among us.
Yes.
Yes, sir.
Dr.
Yes,
Deshmukh
sir, I
has
will
just
check.
told us it was earlier known as ICT
Yeah,
in
exactly.
University of Mumbai.
So,
Thank you, sir. Thank you.
Thank you, ma'am. Do we have any more questions? Just so everybody knows, Dr. Jaspreet has given her email ID in the chat box. So if anybody has any further questions, please note it down and you can be in touch with her. Jaspreet ma'am, I have one question myself from the perspective of many students. While you were doing your PhD, did you face any moment that you wanted to drop your PhD in between because of an issue? And how did you overcome that if you faced any issues like that?
Sir, I faced many times but I have मतलब कभी भी मेरे माइंड में ऐसे नहीं आया कि मैं I should drop the PhD. I will so मैंने actually I have my guide is so very nice, so we have worked.
Thank you, ma'am. My purpose was just so because so many students think that way because of they face many small issues and they just lack the
सर
motivation.
इश्यूज तो ऐसे मतलब आते हैं काफी बट बस ऐसा कि कभी मैंने पेशेंस आई हैव डन विद ऑल माय वर्क पेशेंस सो इट्स फाइन
Good.
Great,
Very good.
ma'am. Very good work. Okay, thank you, everybody. Have a nice Sunday.
Yes, yes. Lastly, 1 minute, Jay.
Sure.
Really, again, I am appreciating Jaspreet for the very good topic on this Sunday.
थैंक्स सर
People have enjoyed. All people also got benefit, as well as Jaspreet also got benefit by answering the questions of eminent personality. So this dialogue should be continued. That is our, as Dr. Prakash has told, awareness is important.
Yes.
And we are trying to create an awareness. So thank you everyone for cooperating in this, our effort. And we'll continue these efforts. Now, within half an hour, there is a lecture series, Indians speaking from abroad. Again, at 2 p.m., there is one more lecture, how to obtain travel grant for international conference. So like that, continuously Microbiology Society is doing efforts. Again, I'm requesting all members to join the second and third lecture today on 12:30 and 2 p.m. today. Thank you. Thank you again.
Thank you. Thank you, Deshmukh sir.
Thank you.
Thank you, everybody. Thank you, ma'am. It was a very nice presentation and great brainstorming session afterwards. Thank you.
thank you.
The Afrin is telling, ma'am, will you give any certificate related to this webinar? So answer is no. We are
Only-
not giving certificate to the attendee. Because this is for only updating your knowledge. And that is the certificate to everyone. No special certificate we are giving. Okay? Thank you. Thank you again.